Welcome back to another HVAC-Engineering-Techie channel training video. Today's training video is on chilled water central plant system sequences. Now, this is probably the most common sequence that people have to deal with on central plants. So we're going to go through all those today. Remember that this channel talks all things HVAC, engineering, design, construction, equipment systems, test and balance, controls, efficiency, and performance. And these sequences are all based upon controls and energy performance. So I'd like to ask you a favor before we go on. If you wouldn't mind becoming a subscribing member by tapping the subscribe button down below, giving me a thumbs up if you're happy with the videos. This costs you nothing, it's absolutely free, but Google uses that data to evaluate these videos, and that keeps me on the air. I would really appreciate it. All right, let's get started on the exciting world of central plant chill water sequences. Thank you. All right, so let's take a second to just review the control videos we have available. Probably have already seen this, but we'll go through this quickly. C1 is our control system basics. A person should take to learn the basic concepts and language about controls. C3 is DDC control architecture. What does the architecture, what do the networks look like? And C4 is DDC control components and devices, those devices used for the network. C5, DDC control installation of wire, how you actually wire up the stuff, and what's important. There are certain things if you do wrong will really mess with your system. Water-cooled central plant sequences, C6. C7 is hot water central plant system sequences. C8 is this one, chill water central plant sequences. C9 is constant volume air handler control sequences. C9 is constant volume air handler control system sequences. C10 is VV air handler control system sequences. C11 is outside air handler control system sequences. C12 is how to tune loops, which is important. C13, how to select and size control valves. C14, how to select and size control dampers. And C15, HVAC pneumatic controls. Now, I know you say we don't use pneumatics anymore, but we do actually. And we'll show you what components are normally used nowadays. Now, the sequence series, these C7 through C11, are basically how to do in-depth sequences for resets and how to get basic energy efficiency out of central plants that aren't so complicated that they can't be used. Now, these sequences also rely on ASHRAE Guideline 36 to show how to make these resets work so they don't have problems. So it's fairly intense and fairly adept. I hope that helps. All right, control sequences. The main technical resource used in this presentation is ASHRAE Guideline 36, 2024, like I talked about. It's for high-performance sequences of operation for HVAC systems. Also utilize standard industry practices. Not everything's in Guideline 36. Well, maybe that's Guideline 36's problem. They try to put everything in there. It turns out to be really very difficult to read because it has a standard sequence, and then they have 42 to 50 modifiers to that based upon another condition, and it gets very, very cumbersome to look at. So I've tried to simplify that for the sequences that we'll show. Hopefully that'll help. Normally, the design engineer describes their desired sequence of operation in standard language on the drawings or in the project specifications. But there are issues with engineer design sequences. New innovative sequences never used before. You know, in today's world, especially in the green building movement, they give you points if you could dream up something no one's ever seen before, thinking that, of course, they would be better and more efficient, but many times those new dreamed up sequences have holes and problems all over them because they've never been done before. So when I tell an engineer, if you're going to create a super duper brand new sequence that no one's ever seen, you need to put enough money in your project to train everybody, to train the owner, his operators, to train the commissioner, to train the test and balance guy, and train the control programmer exactly how your system's supposed to work and what different parameters may be to that. If you don't, they're not going to know, and it will not work. Incorrect logic or logic components. You know, we all forget, even those of us who've been around controls for a long time, sometimes forget that things are connected in physics beyond what we're doing. So especially this applies, especially if you're trying to do a dual reset if you're trying to reset temperature and flow at the same time. And we forget they're connected, so what they're doing down there is not what you're doing, so they may be fighting you big time, so you have to make sure that your sequences are such that it doesn't get messed up by the physics of the air or water. Too complex for successful implementation. Simple is always better. Simplest is always best for many reasons. One is it's easier to do, and people will probably get it more accurate and get it better. Two, it's much easier to keep operating if it's simple. So if you create a sequence that's so complex that it can hardly be programmed, it will be a sequence that can hardly be operated either. So I recommend you keep your sequences simple. And the truth is, there's not many requirements for new sequences. Trust me, we have plenty of sequences out there to do anything you could possibly imagine. So my reference is always to convince the engineer, let's try to use some standard sequences from the manufacturer. They've done them, they've tested them, and they've been tested in the field many, many times over. So that's a good shot those are going to work well. So the way this is supposed to work is controlled submittals are supposed to include a rewritten sequence that includes all the details required to produce the engineer's desired sequence, or supply a manufactured standard sequence that has been fully vetted for actual performance. Unfortunately, what most control contractors do is they cut and paste the engineer's plain English sequence into their submittal, and the reason is they're afraid the engineer will disapprove them if they don't do that. Well, what happens, all of a sudden, as a commissioner, I'm sitting there with a sequence that has no entrance and exit points, it has no timers, it has no loop reset parameters, it has many, many things missing out of it that has to be added by the programmer. So we will know actually what he's programming. If we don't know what he's programming, we really don't know how to test it. And what that leads to is many times causes the test to fail. So please, we need to know the actual sequence the programmer is going to write, not the English language one the engineer's written. That's what it's supposed to do. Now let's create a sequence that makes it actually happen. All right, what should be in a standard central plant chill water sequence? Well, operating schedule, it should have an occupied schedule, conditions for start and end time. An unoccupied schedule, it should have environmental set points for occupied and unoccupied conditions. Room set point, dead bands 1 to 3, or chill water or hot water dead bands. Now, some green building movements I see are asking for 4 degrees dead band, and I don't really recommend that, especially for air systems. People can't really feel 1 degree. They think they can. They really can't. 4 degrees, they can feel it big time. So if you put a 4 degree dead band, the people in that space are going to get hot, uncomfortable, they're going to get cold, and they're going to get hot, uncomfortable. It's not a recommended procedure. Oh yeah, it'll save you some energy, all right, but it's not recommended. So here's standard guideline 36 set points. An occupied space, cooling 75 at 50% relative humidity, heating 70 degrees at 35 humidity. Unoccupied, they say cooling 90 degrees and heating 60 degrees. I'm a little skeptical about 90. I don't like to go that high. I normally don't go below 85, 84, 85. And the calculation you have to do to prove what that is how much energy do you use getting from the setback temperature to the setup temperature versus how much you save using that higher reset for the unoccupied period. And of course, what you want to do is you can reset it as high as long as the recovery period is using more energy. You have to, the building is unique, so you have to calculate it for that building. But my gut feeling is 85 is a much safer bet than 90 degrees. Electrical mechanical rooms, of course, are just 85, 65 because they're cooling equipment, not people. Operating rooms are 65 degrees sometimes and 80 degrees sometimes, depending on what they're doing. And data centers are 75. Well, data centers used to be 75, but they are changing nowadays. The data people used to tell us that the processor, chip processor, needs cold air. We'd like to have 68 degrees. We'll settle for 72, but we'd really like to have 68 to get them to run better. But in recent years, they discovered that those things run good at 95. They don't need 68 degree air. So nowadays, we're able to pump 75, 78 degree air into the room, make the people comfortable, and the processor still will run below 95. Standard default for water temperature set points. Condenser water is 75 for occupied. Heating is 75. We don't have heating for condenser water. For chill water systems, 44 degrees is standard. Unoccupied at 50 degrees. Hot water systems, 130 degrees or 90 degrees unoccupied. So those are standards that are right out of Guideline 36. So other control sequences: start, stop, sequence for startup, sequence condition for shutdown, optimal start condition, optimal start conditions. You could do a central plant with optimal start. That doesn't do as much as air systems, but you could. Because what happens is when you have a system like a building with a lot of mass and you're going to use air to cool that space, it takes time for the mass to get cooled by the air. But in a chill water system, it's very well contained to just the water in the pipes and the heat of the pipes, and the chill water can change it very, very quickly. So to tell you the truth, we don't normally use optimal start in a chill water situation because it's only a few minutes before the water gets cold anyway. Chill water supply temperature control sequence for both cooling and heating, temperature control reset sequence. Chill water pressure control, supply pressure control sequence, supply reset sequence. And where people have gotten in real trouble in the past is doing both of these together. And Guideline 36 has offered a solution to do that this don't get all messed up by the physics of the water. Operator data trends. What data trends does he need to operate the plant? Sensor data, runtime, and operating alarms. What does he need for those? Most important items for energy reduction of chill water plants is the chill water set point maintained, set point resets maintained, the condenser water set points maintained, condensed water set point resets maintained, loop tuning, make sure all the loops are tuned. They must be fully commissioned, or else you may have a big problem. Occupancy schedule strictly maintained. Operations committed to maintain operators of the above. So we need persistence. We need to make sure these things are all set. Now you say, well, why are you saying this? Well, what happens a lot of times in operations, they're standing in front of a customer that says, I'm uncomfortable, you may need to fix it. He can't say, well, I don't know how, I'll do it later when I get around to it, or I'll try to figure out some way to do it, or I'll get somebody who can. Those are really not acceptable answers. The customer's expecting, fix it now. And so sometimes they will. Sometimes they'll blow out a set point and say, well, we've got 45 degree water, I'll change that to 42, and you'll get comfortable much faster. Yes, but he just blew the energy of this plant out of the system. Or we're resetting that up. We're going to just blow out the reset so it'll maintain 42 all the time, and you'll be comfortable. So those are things that can't happen if you want an efficient operating plant. So first one we're going to look at is an air-cooled constant flow chill water system. This is very common in lots and lots of buildings, especially in temperate climates where it's not real hot and not real cold. So here we have a air-cooled chiller, and we have a constant flow system. So the coils have three-way valves, so there's always the same flow through a coil. So these pumps are basically constant volume pumps that come on, do their job, and that's it. So what happens here is the chiller cools down the return water. It goes to the main system pumps, goes out to the coils and back to the chiller, and that's its entire process loop. So here's the point list. Digital output 1 is the starter for P1. D2 DO2 is a starter for P2, and D3 is a chiller enabled and disabled. So this actually starts the plant. Analog outputs is the chiller chill water temperature set point. So our controls is going to tell this chiller what temperature water to operate at, but the chiller itself is doing that through its internal controls. You're just resetting it from an external point. Digital inputs is a P1 status from a current switch, P2 status current switch, and out of the chiller panel, we're grabbing a chiller alarm. In case the chiller goes into alarm, we'll at least know it's an alarm. We may not know what it is, but at least we know it's an alarm. Analog inputs, chill water supply temperature, chill water return temperature, chiller status, how many amps, what load is it at, outside air temperature and outside humidity. Now, we normally run outside air temperature and humidity through the central plant globally for everything else. So normally all the central plants have a weather station to input that data. Okay, typical control sequences. The system shall be enabled and disabled based upon an occupancy schedule. Pump lead lag selection. Lead lag selection of pumps should be based upon operator selection or rotated automatically every 7 days. If any pump fails during operation, it should be locked out of rotation until maintained and placed back into operation by an operator. So once they go down, they're locked out until an operator takes care of the issue, whatever it is. Cooling control. The occupied chill water supply temperature set point should be 46 degrees. The chiller internal temperature control shall control the chiller leaving water to set point temperature. During the unoccupied time, more than 10 net requests are received for more than 3 consecutive time intervals. Start the lead pump and enable the chiller. The starting unoccupied chill water set point shall be 48. Now, these set points I'm giving you, they can be anything. You can change them. The range of the set points, like this is 44 to 48. This could be 45 to 47. So it could be 1 degree that said, oh, this could be 44, which I usually have it. So, I mean, you can change these set points to anything. These are resettable by the operators. Just so you know that this not always exactly what I have here. It can be whatever. Now, the ranges are somewhat typical. 2 degrees, 3 degrees, 4 degrees, something like that is fairly typical. Now, there's another option, starting set point option. Reset the occupied starting chill water supply temperature based upon the outside air temperature. Reset the set point from 40 to 60 degrees when the outside air temperature is 100 to 75 degrees. Reset the occupied chill water supply temperature set point from 48 to 60 when the outside air temperature is between 95 and 75. So now these have this reset. And again, these temperatures ranges are you select. You would tell me what you want to do. You know, if you think this is too cold, then it can go warmer. So I set down to 40, which is minimum supply temperature. You really should never go below 40 because you're getting right close to a possibility of a freeze up on the evaporator, because it has a 4 or 5 degree range, and you need to be really careful that you don't get into that offset. But that's possible too. So then when you come to work and it starts up, it's going to be at approximately the right chill water temperature set point. Or you can let reset handle it either way. It's up to you. All right, temperature reset control. If the system pump flow is confirmed, then reset the chiller temperature set point by using a trim and respawn control logic loop every 3 minutes. For each control valve that are greater than 99% open for more than 5 minutes, send 3 temperature change requests. For each control valve that is greater than 97 open for more than 3 minutes, send 2 change requests. For any control valve that is greater than 95% open for more than 3 minutes, send 1 change request. For any control valve that is less than 95% open, send 0 change requests. Don't send a request. Reset range would be 42 to 50. Now, see, I had that other set to 40, which is probably too cold. So 42 to 50 is a really high range. Now, again, these are totally operatable, selectable, and 50 may be a problem if you're doing dehumidification with this water. So if you're in a very humid climate, 50 degrees is too high of water. It won't dehumidify enough. This probably needs to be around 45 minimum. You need a 55-degree coil to do dehumidification adequately. So you have to do that. Another thing I've always done is I put a dehumidification loop in the air handler that when it's in dehumidification mode, it signals the central plant, I need cold water, and it resets the chill water based upon that humidification requirement. So just to know, these are variables to do that. But this is guideline 36. Now, there might be a problem here. I don't like this, but it did come out of 36. Is every 3 minutes looking at it. But it says this first one, if it's 99% for more than 5 minutes, that actually should have been 6 minutes. So it's 2 periods. It has to have 2 periods to send these 3 temperature requests. Now, the way this all works, we're adding up all these temperature change requests for a 3-minute period. And as many as those we give in that 3-minute period, that's our total request for change. And then we're going to use it in this mathematical calculation to actually change the temperature of the water. So what happens here, this is our chill water supply temperature reset loop parameters. These are the parameters for this particular reset. The set point is 44 degrees. The minimum set point is 42. The maximum set point is 50 degrees. The temperature different delay time, so when it first starts up, it's going to do a 6-minute delay. And that's just to let things get settled out in the building before we start resetting something. If you only waited 3 minutes, you might do something that you didn't need to. Now you have to reverse it. So the 6 minutes is to give things time to settle out. And of course, all these are changeable. So you may say, well, I want 10 minutes before. That's strictly up to you. The time interval is 3 minutes. That 3 minutes is, again, changeable. This one here is ignored request. So what it does is when it gets a request, it doesn't make immediate changes. It has an ignored. So you can kind of, what all these factors are is ways to modify the basic sequence, like at the maximum, at the minimum, to kind of shape this response the way you want it. So this ignored request is 3. Now, they recommend you change this number be set to 10% of your total connected valves. So I'm saying I've got 30 valves, so this is going to be 3. And they said that they've tested this, and this guideline 36 recommends that 10%. So here it is right here. It says initial setting at to 10% of total connected zones or hot water valves. Adjust, or chill water valves, adjust to balance responsiveness to demand. Fewer ignores versus energy efficiency, more ignores. So if you ignore more, you're going to have energy efficiency. In other words, you're not going to lower the water near as fast. Change request, that's the actual change request that your system develops. And then this is the action loop. So if you have your set point resets, and your set point resets or the loop reset action lowers the temperature. So reset would always be going with the energy. So resets always increase the energy when we reset. So that's a 0.25 degrees. We're going to reset it. Each step is 0.25 degrees. So the maximum set point we're going to allow is 1 degree. So in other words, if you had 7 requests coming in and you ignored 3, right? So that's 4. So then you could go up. It would be 4 times 0.25, which would be 1. So that's maximum. But let's say you had 10. Well, you would have more then, but you can't do more than 1 because that's the maximum. So we're only going to let it make a change in a 3-minute period of minus 1 degree. And trim, set point trim is when you're going the opposite way of your reset. So the loop action then would be 1 degree higher. Now, these are settable however you want it to do. If you want it to go up faster, then this would be a bigger number than go down faster. It depends on what you want. Normally, we let the go down more energy fairly quickly because that indicates we have a higher load and people are going to get excited if we don't get there a little quicker. And then the reset normally is less because you take it time or more. So it's all up to how you do these. I think these work, and I have a way of testing this, and I'll show you that in a second. So now remember, this is a constant volume, so we're not going to reset flow because it's constant. So we can reset temperature, which will save us some energy and will make the system operate better. And here's my little handy-dandy chart. Now, all I'm trying to test here is how fast, say if we start up at our normal 44 degrees, how fast can we get down to minimum in case there's a huge load that we didn't predict? So in this particular one, what happens is it's going to ignore these first 2. That's that 6 minutes time delay. So we've time delayed, and now we're measurement. Now we add up our request, and we take that request and we subtract the ignored request is 3, and then we end up with and we had a bunch of them come in, so we have a full 4. We're going maximum, so 4 maximum, 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 maximum. So we got there at just 1, 2, 3, 4, 5 steps. So it took us, from beginning, it took us 18 minutes, which is acceptable. And that's what I'm trying to test here. Because when I used to do these manually before I looked at 36, I dreamed up ways of doing this. And sometimes it got way too long. It might take an hour to get somewhere. Boy, that's not good. It will not work. People will be unhappy. So this will work. It's fast. Once it gets to the bottom, it depends on how the resets are coming in. If the resets are still positive and it wants to reset this temperature down, it can't because it's at minimum. It goes until now all of a sudden where we're getting no resets. So now we're in trim mode. And as we start trimming, it starts walking up at maximum trim. until it gets to total, which in this particular case is 50 degrees. Now you may have set this at 48, so maybe 48, but the times are small. So this is 21 minutes, and 21 minutes is doable. Really, the reactions from tenants and everything, a half hour is reasonable. If temperature goes out of range a little bit and in 15 minutes it comes down, you're not going to have any big complaints about that. And this will actually, these are maximums. I've preloaded enough resets up here to make sure I get this happening. Normally, this will come down in small steps and go up and go down, go up and go down, and not do what I'm doing here. But this is showing the worst case, and that's what I want to see. I want to know what the times are. So this does work for that, and this shows it very clearly that it will work. Remember, you can trim this and test it the way you wish it, but these are good. These will work. These will work well. Monitor trend points. Monitor all temperature sensors. If the condensed water, chill water temperature is above or below set point for more than 5 degrees for more than 15 minutes, send a level 3 trouble alarm. Now, trouble alarms. A level 1 trouble alarm is a life safety issue. Bells and whistles should be going off everywhere. This is an alarm. This is serious. It needs to happen now. A level 2 is an alarm that an operator must get up out of his chair and go do something. It's not like a life safety, but it's something he's going to have some unhappy people if you don't get this taken care of. So he has to get up out of his chair. A level 3 is a trouble alarm. He needs to be aware, and he needs to get it taken care of eventually. But it's not critical to be done right this second because the system is still operating. And level 4 is basically a light trouble alarm that he may or may not, he doesn't need to get out of the chair at all. So normally everything is between a 1 and a 3. All all equipment run failure is a level 2 alarm. That's something you need to get out of your chair. Data trend chill water supply and chill water return temperature continuously with an interval of 15 minutes. This gives an operator a tool to be able to look at what's going on in his system. It's way too long of a period to do real diagnostics, but it's going to give you a hint of what's going on and you can get a general idea. Data trend the outside air temperature and humidity continuously with an interval of 15 minutes. And by continuously, it lets you, it doesn't take a very big file to store a whole bunch of time, because our data control, we can store a lot of data nowadays. Data log run times of all motors resettable by operators for maintenance, so they need to know the runtime of their motors. All right, so now let's look at constant flow chill water systems, which this would be a water-cooled system, which is different than the one we just showed. So in a water-cooled system, we have a chiller and we have 2 condenser pumps. And when the chiller is to run, the condenser pump comes on and flows water across the cooling tower. So what it does, it takes water, pressurizes it, runs it through the chiller and back to the tower. It flows across the top of this tower that has fill in it. And now it's an open system, so it was closed. Now it's open atmosphere. And as this water wets these fill, and the fan comes on, it's pulling air through that fill, and it evaporates the water, and that makes the cooling effect. So that's how the cooling towers work. This is the constant flow side of the system. This system, and so you can see these are system pumps, and the chiller cools the return water, and it goes to these pumps, and it's pumped out to the coils, and you can see these coils all have 3-way valves, so the water flow never changes, whether it's going through the coil or around the coil. It never changes. It's a constant flow system. That's how they work. Okay, set points. So DO1 is system P1 start stop. DO2 is system P2 start stop. DO3 is a condenser P3 start stop. DO4 is condenser pump 4 start stop. DO5 is a cooling tower fan start stop. DO6 is a cooling tower start stop. Is the chiller start stop, I'm sorry. AO1, analog out 1, is a cooling tower fan speed control. You'll notice that the cooling tower has a VFD on it. And all cooling tower fans should have VFDs. You shouldn't even consider it without a VFD. And the reason is that they do 2 things. One is cooling towers very seldom run at full load all the time. So you can save enough energy to pay for it in about 18 months, 15 months. It got to where I stopped calculating them because I calculated every one, and they all came in excellent paybacks. You wouldn't consider it, but more importantly, they also protect the motors and drives. So if you have a gear drive tower, you got to have at least a VFD or a soft starter, either one, so it doesn't put pressure on those gears. Or if you have a belt drive, give it a break and put it on a VFD or a soft start so it doesn't stress the belts. Okay, so and then we have out to the chiller set point. We're resetting this chiller temperature from our system. Digital inputs, P1 status, P2 status, P3 status, P4 status. DI5 is a cooling tower fan status. DI5 is a chiller status coming off the chiller panel. Analog inputs is a chill water supply temperature, chill water return temperature, cooling tower water temperature, cooling tower return temperature, outside air temperature, outside humidity temperature, cooling tower speed, what speed is the fan running, and chiller load in amps, how much is the chiller loaded. This is the data we need to run the central plant. We can have a lot more points, but these are the ones we must have to do what we have to do. Okay, the plant should be enabled and disabled based upon an occupancy schedule. Start the lead condenser pump and the lead system pump when in the occupied mode. If after 5 minutes the lead condenser or system pump current sensor status point indicates no flow, then start the lag pump and alarm the lag pump failure. If any pump fails during operation, it should be locked out of rotation until repaired and placed back into rotation scheduled by an operator. Condenser control. The occupied condenser water supply temperature set point should be 85 degrees. The cooling tower fan shall modulate to maintain the condenser water set point. If during the unoccupied schedule the chiller is enabled, start the lead condenser pump, enable the chiller. And this is exactly how it works. Here's the condenser water temperature. We have 85 here as our set point. So if the water gets up to 87, the fan is at full speed trying to cool that water down. Gets to 83, the fan is at 12 hertz. And if the system continues to go below that, the temperature goes to 82 down below, then we would shut the fan off. Because remember, VFDs have 2 points, start, stop, and speed. Low speed will not shut off. A VFD got to turn it off. So that's points that we have to do in that system. Condenser water temperature reset option. There is another way to do the temperature. Reset the occupied start condenser water temperature based upon the outside or wet bulb temperature. Reset the set point from 85 to 10 degrees above wet bulb with a reset range of 60 to 85 degrees. Lower the reset range needs to be above the lowest temperature that the chiller will function. So what we're trying to do is, what happens, system efficiency is based on chiller lift. And the lift is the difference between the entering condenser water and the entering chill water temperature. So we want that to be as small as possible. To do that is we need to reset the chill water up and reset the condenser water down. Now the chiller starts getting real efficient. And it's been found through some studies that when you reset the condenser water temperature down to 10 degrees above wet bulb, now you can go colder if you want. You can go 5 degrees above wet bulb. What it does, though, is that depends on where you live. You know, if you live in the real high, if you live in the Florida Keys, you're not going to have that low wet bulbs to really get to, so maybe 85 is okay. But if you live where I live, we see 35-degree wet bulbs, not a problem. So 10 degrees is too cold to water, probably, so it can be reset. But what happens is when we're resetting this down, we start saving a lot of energy because we're lowering that lift function. And this works really well. There's a plant here, it's a 20,000-ton plant, who ran 1 year one way and ran the next year that way and compared the weather data. And they saved a lot of energy. Now, what happens, of course, is when you lower this temperature, this fan starts to run more. But with this fan running more, which is much smaller than the motor in here, it makes a difference, but not a very big difference. Still best to lower the lift of this chiller as much as possible, even though this fan speeds up a lot. It runs at high speed much more than it normally would. Okay. Cooling control. The occupied chilled water supply temperature set point should be 44 degrees. The chiller internal temperature control shall control the chiller leaving water to the set point temperature. If during the unoccupied more than net 10 net requests are received for more than 3 consecutive time intervals, start the lead pump and enable the chiller. The starting unoccupied chiller set point should be 50 degrees. If you're in the unoccupied period and your system plan is off, then you can start it by watching how many change requests you get, and then you can go through a sequence of startup. Now, if we do 10 net requests for more than 3, which would be 9 minutes, it will start the central plant, and then the shut-off period would be reversed. So that is a way to do it if you need to do that. If you have tenants that can do that, otherwise you don't need that. Starting set point, reset. Reset the occupied starting chill water temperature based upon outside air temperature. Reset the set point from 44 to 60 degrees. Now, again, 60 degrees tells me that we don't have any dehumidification requirements during real moderate temperature times. When the outside air temperature is 100 degrees to 75 degrees. So from 100 degrees, at 100 degrees, our temperature will be 44, but at 75 degrees, it'll be 60 degrees. Now, maybe that needs to be lower depending on where your building is and what the conditions are. Reset the unoccupied chill water temperature set point to 48 to 60 when the outside air temperature is 95 to 72. So basically, you can change those set points, and all this is doing is making your starting set point a little closer to where it should be. Otherwise, it's going to get there fairly quickly with the resets we're going to do, but this is an option for you. Okay, so now we're going to talk about reset control for this system. Temperature reset control. If the system pump flow is confirmed, then reset the chiller temperature set point by using a trend respawn control logic loop every 3 minutes. For each coil control valve that are greater than 99% open for more than 6 minutes, send 3 temperature change requests. For each control valve that is greater than 95% open for more than 3 minutes, send 2 change requests. For any control valve that is greater than 95% open for more than 3 minutes, send 1 change request. For any control valve that is less than 95% open, send 0 change requests, or don't send a change, rather. Reset range should be 42 to 50 degrees. Now, here's the parameters for this. So the set point's 44, starting set point. Minimum is 42, maximum is 50. Now, remember, you can change these whatever you want. If 50 is not cold enough for reset, for a dehumidification, you might change that, or you might have the dehumidification sequence reset this again, so it can change this set point. Time delay is 6 minutes. The interval is 3, and again, this is 10% of our connected coils. We have 30 of them. Ignored requests are 3 requests, and that's set at 2. Initial setting is for 3, for 10%. If you want to adjust the responsiveness to demand, then fewer ignores. So if you want this to be more responsive, then you have fewer. If you want it to be higher energy efficient, then you add more, and that's what those are for. So then the resets are the resets requests we get from the system. Then this is the set point resets, and this lowers the loop, lowers temperature. That's the reset is lower the temperature. The maximum is 1 degree, minus 1 degree is the maximum reset. In other words, to get this, we take the number of resets, multiply it times, we take the number of resets we get, subtract the 3, and then we multiply that times this, we get the total resets received, but we limit it to no more than 1 full degree. That's what we can do. And then when we trim, which we're going higher temperature trimming, it's 1 degree also. And you could, if you want trimming faster or slower, you change these so they're not equal. And that's up to you, how you want that response of that loop to be. And the formula is if the resets are greater than the ignores, then the temperature is R minus IR times the res value, this res value. So 0.25, we're going 0.25. So if you get 3 of those, it's 0.75. You get 4, it's 1. If you get 5, it's still 1 because it's the maximum. All right, and the tolerances for these limits are, for time is plus or minus half a second. Temperature is plus or minus 0.10 of a degree, and speed is 0.5% of speed, or 3 hertz. So those are the limits, tolerances for these values. And then this is the chart I use to tell how fast and slow the determination time is. So for this one, if you have 44 degrees and it comes out to 6-minute wait time and 3-minute measure time, if it's getting reset requests past the ignores, it drops 1, waits 3 more minutes, it's got more, it drops down. Now it's at minimum temperature, 42, and now it stays there until it gets an increase, and now it starts increasing. Now this again was faked out up here, so I could tell what the maximum speed, these could actually change. And we can see that it's only 21 minutes from here to here. So it's only 1, 2, 3, 4, it's only 12 minutes to get to the coldest water. And then they can get, in 39 minutes, it can get from 42-degree water clear to 50-degree water, which it's doing it in steps, but it's doing it fairly quickly. So those are all well within limits of this half-hour time frame we're talking about. So, and remember that normally this would just bump around 1 degree at a time, or a quarter of a degree at a time. As it goes up and goes down as it needs to be. But these are the maximum loops. You don't want to get these too long. If it takes an hour to get where you're going, it could be a problem. So this is just a test, and this is how it will work. All right, maintain the temperature sensors. Monitor all temperature sensors. If the chill water supply temperature is above or below a set point for more than 5 degrees for more than 15 minutes, send the level 3 trouble alarm. Monitor the condensed water temperature sensors. If the condensed water temperature is above set point by more than 5 degrees for more than 15 minutes, and level 3 trouble alarm. Alarm all equipment fan failure, or all run equipment failure for a level 2 alarm. Data trend the chill water supply and chill return temperature continuously at 15-minute interval. Data trend the condenser water supply and return temperature continuously for an interval of 15 minutes. The data trend outside air temperature humidity continuously with an interval of 15 minutes. Data log a runtime of all motors resettable by operators for maintenance. Data log a running total of requests per week generated by each zone to identify zones that are driving the reset logic. So this is a report I've always done. I would normally do this on a weekly basis. You could do it on a monthly basis if you want. But what it's doing is it's taking and trying to find that zone that is always generating tons of requests. Why is it generating more requests? So you just simply record the number of requests by zone. And if you get one that's 10 times everybody else, that one's driving a reset, you got to do something about it. It's got something wrong. It could be flow. It could have a flow problem. It could have a clogged strainer. It could have all kinds of problems. It could have a balance problem. You need to go look and see what's going on with that one. And that, because as a general rule, they should be all operating within a mid-zone. So many requests to go up and down, but you got 1 or 2 that's crazy, or it may be a zone that you don't even want in this. You want excluded, so maybe it's a electrical room, and you certainly don't want an electrical room driving your reset, so you would remove that from your seek and response sequence. You don't even want to look at it at all. All right, so now we're going to talk about a variable flow primary, secondary chill water system. This is traditionally the way to do variable speed systems. This has 2 secondary pumps that have VFDs, and these are pump water from the central plant into the coils. And you notice these coils all have 2-way valves. So as they need more water, they open up or close down, thus making variable flow in the system. So these variable pumps can speed up or slow down to make this differential pressure sensor at set point. So this flow varies. The primary pumps takes the water, return water from the system, cools it, and returns it to the primary pumps that pump it to the secondary pumps. Now, as this volume goes down, this primary pump flow, which is constant volume, will now go through the decoupler in this direction. If for some reason, which in one chiller it really can't, but if it was, then the system could go this direction. So that's what the decoupler is for. I don't agree with design parameters that make this much smaller than the regular pipe. Might be that you never have it, but to me, it makes no difference. You might as well just make it full size. It'll do what it needs to do. It doesn't need you helping it. I mean, being too large doesn't actually make a difference, so I would do it that way. Here's the point list for this. So DO1 is a system P1 pump, start-stop. DO2 is system P2 start-stop. D3 and D4 are the condenser pump start-stops. I see you got these mixed up. So this is actually 5 and 6 are these pumps over here, these primary pumps, and 7 and 8 is the cooling tower fan stop and the chiller start stop. So it kind of messed up the numbering system, but you get what it's supposed to be. Analog outputs of the system pump, P1, P2 speed, cooling tower fan speed control, and the cooling tower bypass valve. So we have a bypass valve out here is on analog control. We'll talk about that later. Digital inputs, we have system pump P1, P2 inputs, statuses, and we have D3 and D4, which is condenser pump 3 and 4 status. We have 5 and 6, which is primary pump status. And we have DI7, which is the cooling tower fan status. We have DI8, which is a chiller status. Analog inputs, we have A01 is the chill water supply temperature. We have chill water turn temperature. We have the condenser water supply temperature. We have a condenser water return temperature. We have outside air temp and outside air humidity. We have a cooling tower fan speed. We have chiller load amps. And we have the DP sensor for the differential pressure on the secondary side. So that's the point list, which is fairly common. This is a pretty simple system. It's traditional. It works well. It's easy to understand. And it's easy to operate. All right, so let's look at the control sequences. The system should be enabled, disabled based upon an occupancy schedule. Pump lead lag sections. The lead lag status of the pump should be based upon operator selection or rotated automatically every 7 days. If any pump fails during operation, it should be locked out of rotation until repaired and placed back in operation by an operator. Condenser pump. Start the lead condenser pump when in the occupied mode. If after 5 minutes the lead condenser pump current sensor status point indicates no flow, then start the lag pump and alarm a pump failure. Condenser control flow. The occupied condenser water supply temperature set point should be 85 degrees. The cooling tower fan shall modulate to maintain the condenser water set point. Modulate the tower bypass valve to maintain a minimum condenser water temperature of 65 degrees, or whatever the chiller lowest temperature the chiller will function. In other words, we want that to be as cold as possible, but remember, some chillers can't operate at 65 degrees. Some take 70, 72 degrees. So you need to understand what the lowest temperature your chiller is. If during the unoccupied schedule the chiller is enabled, then start the lead condenser pump and enable the chiller. So during the unoccupied mode, you want to make sure this starts up. So the reason we're trying to maintain this set point, and we'd like it to be colder than hotter, is because the value of the energy of the chiller is based on lift. And that's the difference between the cooling tower entering water and the chill water leaving temperature. And we want that to be as small as possible. There are only two ways to do that. One is lower the condenser water, two is to raise the set point. And on most systems, we do both to do exactly that. So there is a option, condenser water temperature reset option. Reset the occupied starting chill water supply temperature based upon the outside or wet bulb temperature. Reset the set point from 85 to 10 degrees above ambient wet bulb temperature with a reset range of 65 to 85 degrees. Lower reset range needs to be above the lowest temperature that the chiller will function. Again, we can't go too low because the chiller has a minimum temperature. Primary pump. Start the lead primary pump when the occupied mode. If after 5 minutes the lead primary pump current sensor status point indicates no flow, then start the lag primary pump and alarm lead pump failure. Once the flow is proved, enable the chiller start. Secondary pump. Start the lead secondary pump when in the occupied mode. If after 5 minutes the lead secondary pump current sensor status point indicates no flow, then start the lag pump and alarm lead pump failure. Secondary pump speed shall be modulated to maintain the chill water supply differential pressure set point as set by tab, plus or minus 15 psi. Be higher or lower depending on the system. All right, pressure control. The occupied chill water supply differential pressure starting set point should be the secondary pump speed shall be modulated to maintain the chill water supply differential pressure set point set by tab of 15 psi. The chill water supply point and reset using the following trim and respond loop. Reset range should be from 8 psi to 20 psi. Now, that's, when you're in tab, you can establish what those are. You can say, let's go, our full design flow is at whatever the pressure we need for design flow at all the rested coils. And if you do that and it's 20 psi, that's good. Then go down and have 10% of them open and see what happens. If you can go down to 8 psi, 8 psi is the low number. If it takes 10 psi, then 10 psi would be the low number. So you need to select that. No flow is not an option. You need some flow. And surely some systems out here put a bypass valve, either a three-way valve here or a bypass valve to always have a little mixed water in the mains. And if mixed water is 10 GPM, then this PSI would be whatever that would be. So you always want to mix it. There's no reason to have more pressure in the system than if you don't need it. All right, cooling control. The occupied chill water supply temperature set point should be 44 degrees. The chiller internal temperature control shall control the chiller leaving water to the set point temperature. If during the unoccupied time more than 9 net requests are received for more than 3 consecutive time intervals, start the lead pump and enable the chiller. The starting unoccupied chill water set point should be 50 degrees. Now you can make it much longer than that. You can make it 20 net requests or something. You can make it so it's different. That's up to you. It's resettable. This is just saying that 44 degrees is set point, and at 42 degrees, the chiller will be at minimum load, and at 45 degrees, it'll be at maximum. So it's only got a 2 degrees. It's a very, very close span, but it will do that. I wouldn't make it any smaller. You can make it larger. This could go to 42, and this could go to 46, but that's just the range you set for it. Okay, starting set point option, reset. Reset the unoccupied starting chill water supply temperature based upon outside air temperature. Reset the set point from 44 to 50 degrees when the outside air temperature is 100 to 75. Reset unoccupied chill water set point from 46 to 50 when the outside air temperature is 95 to 75. Assuming that you have an unoccupied load and that you want the plant to run. This is just simply getting the set point closer to where you really want to be. Remember, the reset will cure this by itself, but depending on what you want to do. All right, typical temperature and flow reset control. Now, this is the sequence that really bungs up a lot of people, and I've had a lot of years of fighting this. And so Guideline 36 outlines a method to keep this basically operating simple. The way you do this, you have to lock it up. You cannot let it run free. You can't just do a pressure sequence and a temperature sequence and let it run free because they're connected in physics. So the more flow you have, the less delta T you have. The more delta T you have, the less flow you need. So that's why you have to lock it up. You can't let it run free. So the reset sequence shall reset both the chill water supply temperature and the chill water supply differential pressure using the following trim and respond logic loop. The reset sequence shall be constrained by the chill water supply temperature reset based upon the chill water supply differential pressure speed to provide chill water supply temperature priority. The secondary chill water supply temperature will start at 44 degree set point, and the chill water supply pressure starts at 12 hertz. Now remember, that was determined during balance. With all reset requests received applied to the chill water supply differential set point, the chill water supply differential resets up to meet the demand load. Once the pump speed resets to 60 hertz, the pump speed shall be locked at this set point, and all reset requests should be applied to the chill water supply temperature set points. When the chill water supply temperature resets back to its 50 degree maximum, the reset request shall be applied to the should be chill water supply differential set point until the pump speed reaches minimum speed of 12 hertz. If both the chill water supply temperature and chill water differential pressure are at minimum load for more than 30 minutes, disable the chiller and stop the primary pump. All right, now let's try to make sense of all those words. So this is the loop of what it would look like during a reset. So this is the reset sequences, or reset requests we're getting. And when you start, the pump's at 12 hertz, and the chill water's up here at 44 degrees. Well, by our sequence here, during this period, we'll only reset the differential pressure. So we reset the pressure up until we get to 60 hertz. Once the pump's at 60 hertz, then we allow the resets to start changing the temperature. So basically what we're doing is we're trying to cool the building with as little water as possible. So we're increasing the pump until because we've got 44 degree water. We're trying to cool everything in 44 degree water. Now, if it won't do it, then we'll start lowering the temperature, which increases the energy of the energy usage of the building. We're trying not to do that. So as it goes to here, so now when we get to this point and we go down, our pump's at 60 hertz, and so we get to this point, this is down at 40 degrees cold. So at this set point, we start increasing the temperature of the chill water to get less energy until we get up here to 50 degrees or whatever your limit is. Once we're up here with the temperature, then we start resetting the pump down until it gets to minimum. Then once we're at these 2 points, and if this goes on for a period of time, we might as well shut the plant down. And that's up for you to decide if you want to do that. It depends on how often you're in that sequence. So temperature and flow reset control. Here's the sequence that actually does the reset. Every 3 minutes, evaluate the system reset request. If any coil control valve is greater than 90% over more than 6 minutes, send 3 change requests. If any control valve is greater than 97% open for more than 3 minutes, send 2 change requests. If any control valve is greater than 95% for more than 3 minutes, send 1 change request. If any control valve is less than 95%, send 0 change request or none. Reset range shall be the chill water supply system shall be from 40 to 50 degrees. Reset range for the chill water supply differential pressure shall be from 10 to 18 psi. And here is the reset parameters. So you can see this was 40 degree set point, 40 to 50 range. Time delay is 6 minutes, so we want to start the system, let it settle down before we start making changes. Our time interval is 3 minutes. Ignored request are 3, and remember that's 10% of our connected load. R is our change request, how many we're getting from the system. SP reset is our reset action. And this means lower the temperature. So we're going to lower the temperature 0.25 degrees for every one of those reset requests we get. And our reset maximum is going to be -1. So we're going to allow 4 of these. So in other words, if you get 7 requests in a 3-minute time period, and you subtract 3, because that's your ignored request, and you have 4, and you multiply 4, you come up with 1. So that works. But if you have more, it's still limited to 1 because that's our maximum. Then when we get to trim, we no longer need to reset, we want to restore. Then we trim, which is higher temperature, and that we're going to let it do that. Every 3 minutes, we'll change 1 degree. And then the formulas are, if R is greater than ignored, if the reset requests are greater than the ignored request, then temperature reset equals R minus IR times RV, limited to the res max. So it's just that times that. If R resets are less or equal to the ignored request, then temperature trim equals change set point by trim amount. So it's just that. So this works really easy. You don't multiply anything. It's just every time you get a trim request, you drop it a degree. So what we're trying to do, of course, is energy, make it better. So if we get systems that don't want it, then let's change it quickly. So, and of course, you can change these numbers to make it more towards the side you want it. If you want it to lower temperature quicker, then you can make this larger. If you want it to raise it slower, then you can make this smaller. So that's whatever you do with those two. And again, these tolerances are down here. Tolerances or time is a half a second. Temperature is 1/10 of a degree. Speed is 0.5% or 3 hertz. And that's the tolerances for these numbers. And here's the chill water pressure reset loop parameters, which is pretty much the same for all the variable volume flows. So this is the set point. It's 15 psi. The minimum differential pressure set point is 10 psi, and the maximum is 18 psi. And these were established by test and balance. And so this 15 psi would have been where they probably set it. And we'll set the range up just a little bit more so that it can have enough pressure to do whatever it needs to. 10 psi also needs to be established during test and balance, but that'll be a procedure that's not normal. So normally you would, for set to 15 psi, you would test everything at the maximum flow for design flow, and that would be to do that. But at the minimum, probably go down and open only 10% or so and close the rest and see what pressure you need to fulfill that and make that the minimum one, and then go from there. That's kind of variable, whatever you decide to do. So now the integral is 3 minutes again. The dead time is 6 minutes. The request, the sequence is every 3 minutes. Remember, that's 10% of our connected coils, which is 30. R is our change request. Static pressure reset is loop. Res action is higher differential pressure. We want to add 0.25 psi every time. And then maximum set is 2 psi. So we're pretty aggressive. That's 8 requests, so that this will go really, really quickly if we need it. And then the trim, which is to lower the DP, is minus 1.5. Remember that reset always increases energy and trim always lowers energy, no matter what we're doing. So the formula is resets. If the resets are greater than the ignored request, then the pressure reset is R minus IR times the res variable, which is this right here, and limited to the maximum. So if you had 4 requests after you subtracted the ignored, and you would get 4 times 0.25, which is 1 psi. You get 1 psi. If it was 8, you'd get 2 psi. If it was 10, it'd still be 2 psi because we have a limit on it. And then down, we're going to go 1.5 psi every time we don't have a request. So if you have no request, we're going down. So that's basically what that is. Okay, and that's the formulas. If R is less than or equal to pressure trim equal change of set point equals this. So anytime you have less requests than the ignored, so in other words, you end up with 0, then it's going down no matter what. Here are the actions. Here's this 10% of our connected load, and the tolerances again are like the other, is exactly the same as the tolerances up here. And that's the chill water pressure reset loop. And this is the pressure one. It's the same. So we have 15 psi's or set point, 10 to 18 psi, 6-minute time delay, 3-minute time interval, 3 ignored requests. And it's going to change 0.25 psi, maximum of 2 psi, and we're going to trim by minus 1.5 psi. So what we're saying is we're going to get there fast if we need to. We can get there fairly quickly. And so those formulas are the same as up here. So let's take a look at how this looks on my little test chart here. And of course, you realize I've manipulated all these requests up here to try to drive this to its extremes. So this is the extreme. We start at 44-degree water. We have 2 periods we're ignored. We get a 3rd period, and we've got a bunch of requests. It will go up to this amount, and that was for all those requests, and goes up as we get more requests. Now our pump's up to maximum. So once our pump's up to maximum, then it will start to lower the temperature because of the request we're getting. And once it gets to minimum temperature, it'll sit there until it gets no more requests, and it starts to do a trim. And this then trim will walk up like this until it gets to its maximum temperature, and then it will allow this to come down like that to minimum temperature. And then this I've said for 30 minutes. This is where we turn them off after that, so we don't let it limp down there. And then my main concern was the minutes here. 21 minutes to start to get the lowest temperature, and then 24 minutes to get the highest temperature. So those are all within this half-hour realm that I like to see. Now, maybe, from 42 to 50, you don't need a half hour, but basically, if it'll do that, it'll work out. Remember, normally, this just inks along. It just makes a change. It doesn't change super quick like I'm showing it, but I'm driving it to its extremes to make sure this is responsive enough for the user. And these are the formulas. This may or may not help. This is basically the same. If they look at those boxes here that had the responses, these parameters are basically the first condition, second condition, and the action. So this is DP res, temperature res, DP res, temperature trim, DP trim, and this is the set point, and you can look at that and use that if you want. The control guy should really easily be able to figure the math out for his system to do that. But these may help him to do that. So these may help him. So here's the typical monitor. Monitor all temperature sensors. Chill water supply temperatures above or below set point for more than 5 degrees for more than 15 minutes. Trouble 3 alarm. Condensed water temperature sensors above set point by 5 degrees for more than 15 minutes. Trouble 3 alarm. Armor equipment run failure by 2 alarm. Data trend chill water supply return temperature continuously every 15 minutes. Data trend condensed water supply and return continuously for 15 minutes. Data trend outside air temperature humidity continuously for 15-minute interval. Data log runtime monitor capable of operating remains. Data log a running total requests per week generated by each zone to identify the zones of driving reset logic. So simply report saying how many resets did we get from this valve during this period of time. And if you got one that's a lot greater than others, go fix it if something's wrong with it. All right, this is a newer system. This is a variable flow chiller system. It's a variable flow, but it doesn't have primary pumps. It actually has a variable flow chiller. The chiller will allow variable flow to it. Now, the other ones we've looked at, the primary, secondary, it has a chiller, but it's not variable flow. It's constant flow. So basically, this has the secondary pumps. The chiller cools the water that flows to the primary pumps or system pumps. It flows out to the coils and back. And these are variable flow. So as the flow starts to cut down and the flow goes down the chiller, it's not a problem, except Variable flow chillers will not accept flow below 50%. They need to maintain at least 50 to 100% flow. Below 50%, you start causing problems with the chiller. So what we do is we put a bypass in to make sure this always has 50% flow. Now, manufacturers have always recommended you put a differential pressure sensor on this bundle to run that valve, and I tell you, don't do that. It sounds good, in a lab. I'm sure they can set a chiller up and they can put a really good instrument on that, and they can do that really well. But in practicality in the field, it does not work. And the reason is because things are changeable. If this bundle starts to get fouled at all, that pressures are totally different. Now your flow is totally different. My take is always put a flow meter in here. They're cheap nowadays. Put a flow meter in that pipe, and this valve will run to that flow meter exactly. Really slow, really good, really strong point, won't be off, and you won't have to worry about it for the price of a flow meter. And this differential pressure will drive you headaches forever. Do a flow meter. It's the way to do it. And then, of course, the condensers. This is standard cooling tower. Pump suck out of the tower, right to the chiller, goes back over the top, has a VFD with the fan. It's a variable flow chiller. Remember, this has to be purchased as a variable flow chiller. Now, what it actually has is it actually has a flow meter in there, watches this, and it runs its compressor. It changes the parameters of the compressor as the flow gets less and less. So or maybe a multiple chiller with multiple compressor, you don't know, but you have to buy a chiller that's specifically for variable flow. And here's the point list. DO1 is system P1 pump, start stop. DO2 is system P2 start stop. DO3 is condenser pump. DO4 is condenser pump start stop. DO5 is a cooling tower fan start stop. DO6 is a chiller start stop. Analog outputs, system pump speed, P1 speed, system P2 speed, cooling tower fan speed, chiller set point, chiller bypass valve. So this is the actuator for this bypass valve, right? It is bypassing that flow for the chiller. Digital inputs, system P1 status, pump P2 status, P3 status, P4 status, DV5, DI5 is cooling tower fan status, and chiller status. Analog inputs are chill water supply temperature, chill water return temperature, cooling tower water temperature, cooling tower return temperature, outside air temperature, outside humidity, cooling tower fan speed, load amps on the chiller, differential sensor from the system to run these VFDs here, and a flow meter for this chiller minimum flow. So point list, pretty simple. These work fine, except for that DP. Boy, you can really fight that DP, especially if you got multiple chillers. All right, typical sequence. The system shall be enabled and disabled based upon an occupied schedule. Pump lead lag times. Lead lag status of all pumps should be based upon operator selection or rotated automatically every 7 days. If any pump fails during operation, it should be blocked out of rotation until repaired, and placed back in rotation, scheduled by an operator. Condenser pumps. Start the lead condenser pump within the occupied mode. If after 5 minutes the lead condenser pump current sensor status point indicates no flow, then start the lag pump and alarm lead pump failure. Condenser control. The occupied condenser water temperature set point should be 85 degrees. The cooling tower fan shall modulate to maintain the condenser water set point. If during the occupied schedule the chiller is enabled, start the lead condenser pump and enable the chiller. There's a condenser water reset option. We've gone over this before, but reset the occupied condenser water set point based on wet bulb temperature. Reset the set point from 85 to 10 degrees above ambient wet bulb, with a reset range of 65 to 85 degrees. Lower reset range needs to be above the lowest temperature that the chiller will function. This may be 70. 65 is doable, but it needs to be whatever the chiller will maintain. And this will provide you more energy efficiency than just straight 85 degrees, especially if you have systems that run during the winter. Okay, primary pumps. Start the lead primary pump when in the occupied mode. After 5 minutes, the lead primary pump current sensor status point indicates no flow, then start the lag pump and alarm lead pump failure. Prior pump speed should be modulated to maintain the chill water supply differential pressure set by tab of plus or minus 15 degrees, whatever that happens to be. And here you see I have 15 psi as a set point, and at 13 psi it's at maximum hertz the pump motor, and at 17 PSI, it's at minimum. So that's just the fan. The pump is going to modulate between those, trying to maintain that 15 PSI set point. Chiller flow control. A chiller chill water flow meter shall modulate the bypass valve to maintain a minimum of 50% evaporator flow. And so here's 50%. If the flow goes to 49%, 48%, that valve is going to be open. If it goes to 52%, it's going to be closed. So basically, it's going to modulate right there to maintain 50%. Now, normally that will not be a point because this system is going to be over 52% flow. So it will be 100% flow. Then this won't. It'll be 100% open. It's not going to matter. I mean, it's going to be 100% closed. It won't matter. All right. So that's the chill water flow system. Starting set point option. Reset the occupied starting chill water supply temperature based upon the outside air temperature. Reset point should be 44 to 50 when the outside air temperature is 100 to 75. Reset occupied chill water temperature set from 48 to 50 when the outside air temperature is 95 to 75. And again, that just gets you to a closer set point to start. Your reset will do it anyway, but this is a way to do it quicker. Temperature and flow reset control. Here we go again. The reset sequence shall reset both the chill water supply temperature and the chill water supply differential pressure using the following trim and respond logic loop. The reset sequence should be constrained by the chill water supply temperature reset based upon the chill water supply differential pressure speed to provide chill water supply temperature priority. We're prioritizing the temperature over the pump speed. The secondary chill water supply temperature shall start at 44 degrees. Set point and chill water supply differential pressure starts at 12 Hertz with all reset requests received applied to the chill water supply differential set point. The chill water supply differential resets up to meet the demand load. Once the pump's speed resets to 60 Hertz, the pump speed shall be blocked at this set point and all reset requests should be applied to the chill water supply temperature set point. When the chill water temperature resets back to minimum 44 degrees, all reset requests should be applied to the hot water should be chill water supply differential set point until its pump speed reaches minimum speed of 12 Hertz. It continues at this level, and all reset requests are applied to the secondary chill water supply temperature set point. If both the chill water supply temperature and the chill water supply differential pressure are at minimum flow for more than 30 minutes, disable the chiller. So it's the very same sequence as the other variable flow. And here's the system again. So if we're starting up and start at 12 Hertz, then all reset requests are applied to the pump. Once it's there, it's locked at 60 Hertz. And at this point, we start resetting the chill water temperature till we get down to its minimum, which is 40 degrees. And then on the reverse, we're sitting here at this, so we're pump's still running. And as the resets start resetting this up, gets to here, now we let the pump go down, and here we're at 50 degrees on the chill water and a minimum 12 Hertz on the pump. So now we're at minimum, and if that lasts a long time, we'll shut the plant down. Every 3 minutes, here's the actual reset sequence. Every 3 minutes, evaluate the system reset request. Any control valve is greater than 99% open for more than 6 minutes, send 3 change requests. If any control valve is greater than 95% open for more than 3 minutes, then send 2 change requests. Any control valve is greater than 95% more than 3 minutes, send 1 change request. Any control valve is less than 95%, send 0 change request or no request. Reset range should be for the chill water system shall be 42 to 450 degrees. Reset range for the chill water differential pressure should be 10 to 18 psi. And then here's the reset parameters. So for temperature, we're at 44 degree set point. We have a minimum of 42 and maximum of 50. Our time delay is 6 minutes again. Our time interval is 3 minutes. This loop is going to look every 3 minutes. We have ignored a request of 3, and this request 3 is 10% of our connected load. We have 30 valves, so it's 3. Our change requests are our set point reset, which is to lower the temperature, increase energy, and that's 0.25 degrees. So we're going to do that real slow. And then reset maximum is 1 degree. And so we can't, on every 3 minutes, we will not make a change greater than -1 degree. And then the trim is to go up. We'll let it go up by 1 degree. So we want to trim fast. We want to reset slow because we're trying to control energy. The formula is if resets are greater than the ignored request, then the temperature reset is R minus IR times res value, which is this value. So if you have 7 resets coming in, you subtract your ignored ones, 3. So that leaves you 4. So 4 fighting typhoid is 1. Okay, that works out, 1. But if it's not 4 anymore, it's 8. Still, you can't go above -1. So -1 is the maximum. And then the trend is 1. And of course, the other things are just the same as the tolerance. This is the chill water pressure reset loop parameters, which are the same as the previous variable flow primary secondary chillers, but this is a variable flow chiller, but the pressure reset is the same. So our set point is 15 psi, our range is 10 psi to 18 psi. We have a 6-minute deadband, just like all of them. We're at a 3-minute interval, because that's what we've established. We have a ignore request of 3, and remember that's 10% of our connected coils. And we're going to reset our static pressure every time. For every reset of 0.25 psi, we're going to go up, increase energy. We're going to have to limit that to no more than 2 psi, which means this system will change really quickly. And we'll let it go down at 1.5 psi. Now, remember, these are all numbers that I've just selected to make sure the reset loop is responsive enough. Now, if you change or reset this ignored request down, it'll get more responsive. If you change it up, it'll get more energy efficient. So that's kind of the thing. But this 10% seems to be the sweet spot. And so the formulas, again, just like it was before, R reset requests are greater than ignored requests. Then it's R minus IR times res variable, which is that. So if you end up with 4 net requests after you've subtracted 3, then you would take 4 times 0.25, which would be 1 psi. So they let you go 1 psi. If it was 8 requests, then it would equal 2 psi. If it was 10 requests, it'd still be 2 psi because that's the maximum limit. So then the less to trim, if R, the request, is less than the ignored request, which meant it'd be being 0, of course, then the change will be the set point trim. So we don't go down slow, we go down quickly because we want to save energy. So if we can go down, we'll go down quickly. Then if we have to go back up, we'll go back up. So that's the process. Remember the 10%, this 3 is 10% of our connected load, and our tolerances are the same, which are time limits a half a second, temperatures 1/10 of a degree, and speed is 0.5%. So those are the same tolerances as before, and that's the chill water pressure reset loop. And here's my little chart to see how responsive this is. So again, if we start at 4 degrees and we start at 15 psi, and we go out here and then we get a change request, we're going to go up, get another change request, go up here. Now we're at maximum, we're at 18 psi. So now we start applying our resets to the chill water temperature. And once it gets down to 42, we're at lowest temperature, and we let it ride until we start getting negative reset request. So in other words, this time interval really doesn't mean anything. This is the system. But now we start going up till we get to the 50 degrees. And once we're at 50 degrees, we let the pump speed come down. And so my take was that this is 21 minutes, which is acceptable. This is 34 minutes, which is acceptable. This total thing is 90 minutes, but you got to remember, this is not part of that. So this will probably get down to about 1 hour. And so to go from 44 to 50 degrees at minimum pump speed now, there's no scenario I can think of would do this. I mean, you would have to have a building that's under maximum load and go to minimum load in 24 minutes. That ain't going to happen. But I'm trying to check the responsiveness of the system. So the system response is good. I'm okay with this. Another way you could do this is stand out in the field, watch it as it happens. But it takes hours to do that. And data trend it, every 3 minutes, data trend everything you want to see what's happening. And if you're commissioning the system. And this is the formulas again. I'm not going to read these. You can clip these out of here. These are the formulas that actually tell you when to go and when not to go. It's actually all in here, the parameters, but this is the actual written ones. Monitor points again. Monitor all temperature sensors. If the chill water supply temperature is above or below a set point for more than 5 degrees for more than 15 minutes, send the level 3 trouble alarm. If it monitors the condenser water temperature, if it's above 105 degrees by 15 minutes, and level 3 trouble alarm, monitor chiller flow, a level 3 trouble alarm, if the chiller flow is below 50% flow set point for more than 5 minutes. So if it goes below flow, that trouble 3 is fine. When the chiller shuts down because it has no flow, it'll be a level 2, and you'll go see what's going on. Alarm all equipment, run failure, level 2 alarm. Data trend, chill water supply and chill water return continuously at a 15-minute interval. Data trend, condenser water supply and return temperature continuously at an interval of 15 minutes. Data trend, chiller flow continuously with an interval of 15 minutes. By the way, all these continuous intervals, it doesn't matter if you want to do that for unoccupied, but you can run them so that they're only running for an occupied period if you ever start during occupied. Either way, it's no big deal. Data trend outside air temperature emitted continuously with an interval of 15 minutes. Data log runtime of all motors resettable by operators for maintenance. Data log running total requests per week generated by each zone. That's to tell which zone's driving the sequence. If you have one zone that's way high on request, you need to go figure out why that is. All right, so this is the last one, and I just wanted to get a multiple chiller with an economizer, water side economizer in there to give you an idea what that all looks like. So this is a multiple chiller, multiple tower, multiple pump variable flow system. This is a primary, secondary, back to the other kind with multiple chiller. And you'll see that the point list is the same, it's just bigger. You've got more equipment. So we have system P1, P2 start stop, condenser pump P3, P4, P5. We have 3 pumps start stop. A primary pump P6, P7, P8 start stop. We got 3 of those. Cooling tower fan 1, cooling tower 2 fan stop. We have cooling tower 1 isolation valves, cooling tower 2 isolation valves. Chiller 1 start, chiller 2 start. We have C1 as a chiller isolation valve, C2 chiller isolation valve, heat exchanger isolation valve, and a heat exchanger condenser water isolation valve. So what happens here is when we're running one pump, we have to have the other valve closed off. If you don't do that, you'll mix water and you'll never get the cold water where you want it. Same with cooling towers. These systems like this are generally that one pump is dedicated to a chiller even though they're headered, and one standby. And normally one tower is dedicated to a chiller, and this one's to this chiller, and no standby. But you can switch them, but normally that's not automatic. It needs to be a little bit more work to do that. And the only reason that makes things so much simpler for operators. You know, if they have a chiller fail, just switch your pump also. It's no big deal. When you try to say pump P1 is running chiller T2, it just gets confusing for operators. So I prefer them to be locked together in software. With a switch, you can change it, but it's just easier to tell what's going on that way. Digital inputs, okay, P1, P2 status, P3, P4, P5 status, primary P6, P7, P8 status, cooling tower 1, 2 status, chiller 1 and 2 status. Analog inputs, secondary chill water temperature, supply, secondary return temperature, primary chill water supply temperature, primary chill water return temperature, condenser water temperature, condenser water return temperature, outside air temps, outside humidity, cooling tower 1 fan speed, cooling tower fan speed, C1 chiller amps, C2 chiller amps, C1 condenser head pressure, C2 condenser head pressure, and differential pressure sensor. Analog outputs, P1 speed, P2 speed, cooling tower fan speed control, cooling tower 2 fan speed control, chiller 1 set point, chiller 2 set point, and chiller 1 head pressure valve, chiller 2 head pressure valve. So what happens here is we have a heat exchanger. And when we want to bring a heat exchanger on, we close the isolation valves of the chiller. We leave the tower on, and the tower is running water through this. And our set point now is maintained by the cooling tower fan. And those work really well, but we have low humidity levels or high elevation, either one. This can save you a whole lot of energy by never having a chiller online. Now, the problem with these is when you want to switch, when you switch back to chiller from heat exchanger, to make this work, we drive this temperature down to absolutely lowest temperature. This may be 45 degrees up here in the cooling tower. Well, this chiller cannot handle 45 degrees under no circumstances. So there's 2 things that I would recommend doing. If this chiller is the one you want to run the central plant on, then I would use this tower system. If you use this tower system for heat exchanger, then you want to use this tower system to run the chiller, because it'll not have super cold water. But if for some reason you have to switch back, we have a head pressure valve on here, and this chiller will manually or will automatically control that head pressure, keep its head pressure up so it doesn't go real low at low temperature. And that will let because all chillers require slightly different pressure. Whatever that manufacturer needs is what he'll get. But that's a safety in there, switching back from heat exchanger. And we'll go through that in the sequence. System shall be enabled, disabled based upon an occupancy schedule. Pump equipment lead lag status of pumps and equipment shall be based upon operator selection or rotated automatically every 7 days. If any pump or equipment fails during operation, it should be locked out of rotation until repaired and placed back in a rotation scheduled by an operator. Condenser pumps are headered, but in software, each chill water pump is dedicated to a specified cooling tower, where the third pump is standby as dictated by an operator. Start the lead condenser pump and open its respective cooling tower isolation valves when in the occupied mode. If after 5 minutes the lead condenser pump current sensor status point indicates no flow, then start the lag pump and alarm lead pump failure. Condenser control. The occupied condenser water supply temperature set point should be 85 degrees. The cooling tower shall be modulated to maintain the condenser water set point. After 5 minutes, the VFD status indicates no flow, then switch to the lag cooling tower and alarm fan failure. If during the unoccupied schedule the chiller or heat exchanger is enabled, then start the lead condenser pump and open the enabled chiller or heat exchanger isolation valve. Again, here's an option that instead of using 85, you could use a reset sequences of wet bulb plus 10 degrees, which will give you a lower cooling tower water, which will increase your efficiency. If in economizer mode, chill water reset should be from 85 to 40 degrees. And you have to remember you've got about a 5 degree offset between the cooling tower, so you're going to have the variable. So you got to have a lower temperature from your cooling tower to get to the heat exchanger, because the heat exchanger has that approach temperature. Primary pumps are headed in software. Each pump is dedicated to a specific chiller or heat exchanger, with the third pump is standby as dictated by an operator. Start the lead primary pump and open its prospective isolation valves when in the occupied mode. Or a chiller or heat exchanger enabled during the unoccupied mode if after 5 minutes the lead primary pump current sensor status point indicates no flow, then start the lag pump and alarm lead pump failure. Once flow is proved, allow a chiller to start. Okay, typical control sequence, secondary pumps. These sequences get somewhat lengthy. Secondary pumps are headed with one pump stated as lead and the second pump is standby as dictated by an operator. Start the lead secondary pump when in the occupied mode. If either 5 minutes or the lead secondary pump VFD status point indicates no flow, then start the lag pump and alarm the lead pump failure. If during an unoccupied schedule more than 9 net requests are received for more than 3 consecutive time intervals, start the lead secondary pump and enable the lead primary pump, condenser pump, and chiller. When no net requests are received for more than 30 minutes, return to unoccupied status. Start a lockout time for 60 minutes to prevent frequent cycling. So that's doing the secondary pump system. Pressure control. The occupied chill water supply differential set point shall be secondary pump speed shall be modulated to maintain the chill water supply differential pressure set point as set by tab, somewhere around 15 psi. It could be 20 psi, it could be less. The chill water supply differential set point shall be reset using the following trim and respond logic loop. Reset range shall be from 10 to 20 psi. And remember that 10 psi is established during tab also. The 20 psi is established, or 18 psi, whatever it is. The maximum is tested when the system is being balanced to design set point. But we need to then pick a set point that's a typical set point, which is much, much less. Say with maybe only 10% of the load open, what is that pressure? That would be the minimum set point we'd set at. Now this is a set point here of say 15 psi is what the tab guy told us. And so that if the pressure is at 17 psi, our pump is down at 12 hertz. When it gets to 13 psi, it'll be at 60 hertz. And this is the loop inside that runs the pump. This is the loop that runs the pump. Chiller cooling control. Chiller are sized so one unit is capable of doing the total building load with a second unit in standby. The occupied chill water temperature set point should be 44 degrees. The chiller internal temperature control should control the chiller leaving water to set point temperature. During the unoccupied time, more than 9 net requests are received for more than 3 consecutive time intervals. Start the lead pump and enable the chiller. The starting unoccupied chill water set point should be 50 degrees for unoccupied. And again, we're running this from 44 to 45. We only have a 2 degree span here, which is fairly close. Normally we'd see a little more than that, maybe 4 degrees, but all we're saying is that when it's at 43 degrees, the chiller load is at minimum. When it's at 45 degrees, it's at maximum. That's all it means. That's going to run to maintain this set point. Again, the starting set point can be based on the outside air temperature. Reset the set point from 42 to 58 degrees when the outside air temperature is 170 degrees. And these are selectable. 42 is fine, 58 a little high. And maybe your system can't handle that. It might be 50. Reset on the chill water set point from 46 to 58 when the outside air temperature is 95 to 70. So what we're trying to do is just get closer to the starting set point, but you don't have to do this because the resets we're going to do will do it automatically. All right, here's this typical sequence. The heat exchanger or water-side economizers is intended to provide the cooling load during colder months without the need to run a chiller and is not intended to run in parallel with a chiller. When the system is calling for cooling control and the ambient wet bulb temperature is 5 degrees below chill water supply temperature set point for more than 5 minutes, disable the lead chiller and cooling tower if operating and open the heat exchanger isolation valve. Open the lag cooling tower isolation valves. Enable the cooling tower fan. The cooling tower fan VFD shall modulate fan speed to maintain the chill water temperature set point as reset by the following temperature reset control. Starting temperature under heat exchanger control should be 48 degrees. Heat exchanger mode occupied chill water supply set point range should be 46 to 60 degrees and 46 to 60 degrees for unoccupied mode. Now, the reason these set points are different than what we talked about in other ones is because this is never going to work. The heat exchanger will never be online during maximum load. It's always shoulder load. And so we're trying to use this. And if you have a system that runs 24 hours, it'll always come on at night. So you need to be prepared for that. These work very, very well in higher temperature areas or high altitude. High altitude, I had a plant at 7,000 feet, and I could run the plant 9 months of the year just on the heat exchanger. The few summer months, the 3 summer months I couldn't, but the rest of the year, this is a manufacturing plant, so we had heat load entire year. So these do work. When the chill water supply temperature rises more than 4 degrees above set point for more than 5 minutes, disable the heat exchanger economizer mode and open the original lead cooling tower isolation valve and enable the cooling tower fan. Open the lead chiller isolation valve and enable the chiller. The chiller will directly control its condenser water head pressure valve to adequately chiller head pressure during the cold water startup. Once the heat exchanger mode has been disabled, start a 4-hour lockout timer to prevent frequent cycling. So this is one you certainly don't want cycling. A lot of them I put in a 12-hour timer just so I want to start it once per day. And realizing it's going to start at 1 or 2 in the morning if it's a manufacturing plant or something that has a schedule of 24 hours. So we just don't want it to shorten cycle every half hour. So that would be, you would lose the building because you would lose the capability. Continually switching between heat exchanger and chillers takes some time. And if you do it too late in the process, if you let the chill water build up too high a temperature before you do that, it takes forever to get down. You have unhappy occupants. Temperature and flow reset control. So we're going to do the same thing we've done for the others. The reset sequence should reset both the chill water supply temperature and chill water supply differential pressure using the following trim and respond logic loop. The reset sequence should be constrained by the chill water supply temperature reset based upon the chill water supply differential pressure speed to provide chill water supply temperature priority. The secondary chill water temperature shall be start at 44 degrees set point and chill water supply differential pressure starts at 12 hertz. With all reset sequences received applied to the chill water supply differential set point. The chill water supply temperature resets up to meet the demand load. Once the pump speed reaches the 60 hertz, the pump speed should be locked at this point, and all reset requests should be applied to the chill water supply temperature set point. When the chill water supply temperature resets back to up to 60 degree maximum or 50, whatever it was, all reset requests should be applied to the chill water supply differential set point until pump speed reaches minimum speed of 12 hertz. If both the chill water supply temperature and chill water supply differential pressure are at minimum load for more than 30 minutes, disable the chiller and start the primary condenser pumps. And here's the actual sequence. Every 3 minutes, evaluate the system reset request. If any coil control valve is greater than 99% open for more than 6 minutes, send 3 change requests. If any control valve is greater than 97% for more than 3 minutes, send 2 change requests. If any control valve is greater than 95% for more than 3 minutes, send 1 change request. If any control valve is less than 95%, send no request. Reset range should be occupied, chill water supply temperature 40 to 60 degrees. Reset range for the chill water supply differential set point should be from 10 to 18 psi. Reset range for the unoccupied chill water set point should be from 46 to 60 degrees. Reset range for the chill water supply differential pressure should be 10 to 18 psi. So this is how it uses those requests to get where it's going. And here's that sequence again. So if we're starting, starts at 12 hertz, the pump speeds up to 60 hertz and locks there, and then it allows the chill water pressure to start decreasing until it gets to 40 degrees. And then as we go back, it resets the chill water back up to 60 degrees and allows the pump to go down to set point. And when they're at minimum for 30 minutes, it shuts everything down. And here's the parameter loop for this. So this is a 44 degree set point, 40 to 60 reset range. Time delay 6 minutes. Startup time delay. Our normal seek time is 3 minutes. Our ignored requests are 3. Remember, that's 10% of our coils. And then we have the R's, our reset request coming in. SP res resets, which lowers the temperature, is 0.25 for every reset we receive. So we're going down a quarter degree. Maximum we will go down is 1 degree, so we'll go down 4 res units if we need to request. And set point trim is +1, so we can go down -1 every 3 minutes, or we can go up 1 degree every 3 minutes. And if these are not aggressive enough, you can make this larger, you can make this larger, you can make this larger, whatever you want. All right, this is the chill water pressure reset loop parameters for variable flow chiller system with a heat exchanger. So this is our big multiple chiller system. And the chill water pressure reset is exactly the same. It's no change. So remember, it's got a set point of 15 psi. We're at a range of 10 to 18 psi. We have a original delay of 6 minutes. We have our 3-minute interval for checking all this. And then we have a 3-minute ignored request, 3 ignored requests. R is the request. Static pressure res is how we reset it up. More pressure takes more energy. And we're going to let it go up 0.25 psi, so it's going to go up really slowly. And then we got a maximum reset of 2, which is, it'll go up really fast. If you have a lot of requests, it'll catch it as soon as it can. And the negative is -1.5. So remember, if you have 4 net requests after you subtracted the 3, your ignored request, you take 4 times 0.25, that's 1 psi. But if you have 8, it ends up being 2 psi, which is your maximum. If it's 10, it's to be 2 psi because we have a limiter on it. And this data down here is the same as before. This 3 is the ignored request is 10% of your connected coils, and we have 30. We note the tolerances are half a second per time, half a second per time. Temperature is 0.1 of a degree, and speed is 0.5, half a percent. So that's the tolerances that this would operate with under. Just so you know that. And that's the chill water pressure reset loop for a variable flow chiller with a heat exchanger. It doesn't change. This is my handy chart to show the reaction to those parameters we've selected. And this would be the set point of 44 degrees of temperature. So when we start our loop, we get a 6-minute dead band right here. So we get two 3-minute cycles. It does nothing. And then in the next cycle, it says, wow, I've got a bunch of requests. But remember, in our sequence we say we limit it until the chill water temperature gets to minimum. Until the pressure gets to maximum, we don't do anything to the chill water temperature. So we're trying to cool everything with this 44-degree set point water. So we apply the resets to the pressure and we let it go up each time. We cycle it, we go up to its maximum of 18 psi. And once we've got there, then it allows the temperature to start dropping. So this sets to where it goes down to the 42 degrees, which is the minimum position. And it goes down and sets, well, that's 40 degrees, it goes down for a time. And then when it gets no more requests and it's time to start trimming, it will then set and trim the chill water temperature until it gets to maximum. Now, this has a super maximum clear to 60 degrees. That may be too warm, depending on the building and what you have. It may need to be 50, 58, 56, who knows. But it needs to be up here because this is a job that has a heat exchanger, has a water-cooled economizer. To do that, we need to reset this water to the highest temperature it'll actually do the job. Now, if 60 is too high, that's too high. But whatever it is, if it's 58, it'll go to 58 and stop. And then we start reducing the pump load by cutting it down to its minimum. And my whole purpose for this was, again, to see the temperature, to see the timing. Now, this up is 30 minutes, which is okay. So, in other words, until when we start, the time to maximum pump is 18 minutes. So that's well within the range of comfort response. And to just get to minimum cooling, which will be maximum pump minimum, so it would be maximum load, is 30 minutes. So that's certainly within the range. And then once we get back, it's going to take 57 minutes to get from minimum 40 degrees to 60 degrees. It's going to take 57 minutes. Now, that's quite a bit, but since we're on the relief side, we're on the trim side, it won't affect the load because the coils will handle whatever the load. If there's no load, they'll shut down, and we'll be just spinning our wheels for a few minutes, but it still won't affect the comfort of the building. And then it only takes 15 minutes for the pump to come down. So these are parameters all within comfort limits of the space, and that's why I use this to kind of check it out. Now, you can stand out in the field and do this yourself. It takes an hour, 2 hours to do this, but and maybe a whole day by the time you get done messing with it. But it's good to know that you can respond. Now, remember, normally these don't do these big chops like this. It would come up and, if the 44 degrees was enough load, it might go up and go down one, go down one, and it could take some time to do this. We don't care about how long it takes as long as it's meeting the load. We do care about how fast it gets there to be able to catch the load. So that's my purpose in looking at these charts. This is the actual programming parameters, and it's basically just to put this in mathematical forms to do what we've already talked about. These may have a few errors in them because this was a really mind twister to come up with these, but your programmer can certainly come up with a program that will allow this chart to do what this chart and what those sequences say. It's not too complicated. I did this because you're not sure what kind of programming the system takes for any individual system. It may be object oriented, it may not. So they may need to have some exact formula. This will actually get this. This is the resets and this is the trims. This is the first category. The first category must be met, and this is the second category. And this is what actually gets trimmed or reset. The monitor points is all temperature sensors. If chill water supply temperature is above or below 5 degrees for 15 minutes, then trouble 3 alarm. Condenser water temperature is greater than 5 degrees for more than 50 minutes, then trouble 3 alarm. Alarm all equipment run failures or level 2 alarm. Data trend chill water supply, chill water return continuously at 15-minute interval. Data trend condenser water and condenser water return temperatures at a 15-minute interval. Data trend chill water supply and chill water return temperatures could during heat exchanger operation with an interval of 50 minutes. We want to see what happened during heat exchanger. So we need to know when that's operating. Data trend outside air temperature and humidity continues with an interval of 15 minutes. Data log run times of motors reset by operators for maintenance. Data trend and running log per week generated by each zone to identify zones that are driving the reset logic. So now we're going to talk about hydronic system set point change suppression. When we do these automatic resets, the way we're doing it with reset request, we need to think about suppression. And here's why I'll tell you what's going on here. So anytime a water temperature set point is reset greater or equal to 1 degree, start a suppression timer that prevents more reset requests or set point alarms for 3-time intervals. If after that the reset condition remains the same or is greater, extend the suppression timer another 3-time intervals. And if after that the reset condition remains the same or is greater, extend the suppression timer another 3-time intervals. Then end the suppression timer. So what this is actually doing is if you have a water temperature set point and you change that temperature set point by 1.5 degrees or 1 degree, and then the interval goes, and it's at the end of that 3 interval, the system didn't actually fix anything. It didn't actually increase. So now, you didn't change the temperature. You had a set point change, but nothing actually happened. So that now the resets get larger, and the alarm persists. So then it asks for more, and then wait 3 more intervals or another interval. It doesn't work. It's going to ask for more. So what happens is it keeps asking more and more and more requests, but the system's not responding. So what it'll do, it'll drive your temperature request all the way to maximum, whatever that is, or minimum, whether your temperature's going up or going down. And that's not what we want to do. That would increase energy proportionally, so we're not doing that. Now, eventually the alarm will trigger. The operator will figure it's not working, but we don't want to drive these resets completely out of sight because of that. And it may not be that it's working. It may be because the mass is so large, it's going to take longer. That's what we're trying to do. Is we're trying to get somewhere around 30 minutes of time of suppression of the alarm and suppression of the resets. So then this is per set point. So if you have a whole bunch of set points, the others may be doing other things, but this one, for each one, you're going to put this suppression formula in place, and it will help it stay stable. And that's the end. I'm sorry about it being so long, but there's a lot of them to cover, and I didn't want to really make a separate video for that. So I hope you endured, or at least go back and look at the ones you won't look at. I do have them chaptered down at the bottom, so you can look at that. So I appreciate you guys really watching them, and I hope you get something. And if you have friends that ask questions, send them to the video. Have a wonderful day, and I'll catch you on the next one. Thanks. Bye-bye.